Hello, everyone. We're going to be going over Chapter 1 in your book, Introducing TCPIP. So, we're going to talk about the history and collection of networking protocols, such as TCPIP, which, if you didn't know, is an abbreviation for Transmission Control Protocol, Internet Protocol. We're going to be talking about the OSI reference model, the TCPIP networking model, references, specifications, and a whole bunch more. The objectives for this chapter are we're going to discuss the origins and histories of TCP/IP, the process by which standards are created, requests for comments, how those RFCs are formalized, and we're going to dig into the surface level of the big difference between IPv4 and IPv6 and why eventually we really have to get everyone on IPv6 and why it is extremely important. We're going to dig down into the OSI reference model, which gives you a design basis for explaining the various layers of a network, as well as the TCPIP reference model. We're going to talk about a bunch of terms in terms of protocols, sockets, ports. We're going to describe data encapsulation, and we're going to look at basic practices and principles for network protocol analysis. So, what is TCPIP? It's a big collection of networking protocols. And what's a protocol? It's a, quote, precise set of standards that governs communications between computers on a network. So really, here, there's two key protocols we're focusing in on. It's TCP, which makes sure that messages get to the recipients and their destination, and IP, which really manages the routing or the addressing of these messages. So there's a big, long background. This is pretty old. So if you don't know the history of the internet, in 1969, we had ARPANET, which was a government project, and eventually it had a packet switch network where each sender and receiver had a unique address, much like your house address. And the packets didn't necessarily have to follow the same path each time they went from origin to their destination. So the design goal of TCP/IP was really to withstand a nuke strike. You want to make sure that no matter what happens to the physical infrastructure, a sender can get a message to a receiver. We want to make sure computers can communicate easily and interconnect systems across long distances. And as we're seeing today, we have interconnections out in space and back to Earth. So we need to make sure it all works all the time. A little bit more in 1978, we had our first instance of IPv4. In 1983, you had the Defense Communications Agency that took over ARPANET, and then University of Wisconsin helped out with name server technology. In 1987, we had a number of hosts on the internet break 10,000, so we were finally going places in the number of servers that were out there. And then in 1989, we broke 100,000 servers, so we're just increasing exponentially here. The Internet Society was chartered in 92. Internet was chartered in 1993. We have spam, online junk mail that tries to get through starting in 1994. And then in 1997, if you can't believe it, 31 million registered domain names. So I know we've gone through a bunch of chronology here and probably more than you really need to know, but it's good to have a background. So, who quote unquote owns TCP/IP? It's completely in the public domain. It's been funded by government money and public money since it was created. So, theoretically, TCP/IP is owned by everybody and nobody. Now, we all know governments can, do their political dalliances, but in the end, really, it is an open model that anyone can use. So standards groups that are important, we have the Internet Society, the Internet Architecture Board, Engineering Task Force, Research Task Force, um, the ICANN, Internet Corporation for Assigned Names and Numbers, which the US just relinquished control of. And just so you know, you should look these up if you're interested. You can join some of these, you can participate in some of these organizations and help formulate the standards that are created. So IPv4 and IPv6, we're going to be talking a lot about this in the course. So we said IPv4 is pretty old, 32-bit address space, and we've run out of addresses. So we're going to talk about later on how we have more addresses, but essentially it really goes down to NAT or network address translation. IPv6 is 128-bit addresses, so you're talking 8 times 10 to the 28th in terms of number of possible addresses you can have. So we'll talk more about that later, but it's going to be huge in the course. TCPIP standards and requests for comments. This is how the sausage is made in terms of the standards and protocols that are put together for TCPIP. You can go online and read all these RFCs. They are long, they are drawn out. At your point right now, probably not super important for you to look at, but if you want to get an idea, go ahead and pop in there and take a look. OSI network reference model, huge, and this is going to matter in all the courses you take. So it's a reference model. It's used to describe things in a common language. It's ISO or OSI in the US. We call it OSI. It was designed to replace the original TCP/IP reference model. And again, it's used to explain how networks operate. TCP/IP is the standard protocol suite of choice, though. The goal of the OSI model itself is to break down each of the major layers in a network and into a computer system so that concepts can be explained in a common language in small bite-sized chunks. We want to separate the hardware from the networking software, and this allows the communication to easily help solve problems. The layers can be treated as operating independently, and a change to one layer doesn't necessarily affect another layer. Individual layers may work together on pairs of computers, and different types of expertise is needed on each layer, both in terms of actual computing systems and network architecture, but you may focus on one layer in your career. TCP/IP is designed to work on this layered model itself. So this is a picture of the OSI model. We're going to go into each layer, but in order to remember it, application, presentation, session, transport, network, data link layer, and physical, you might want to go ahead and employ a mnemonic device. So for instance, please do not touch Steve's pet alligator. Please do not throw sausage pizza away. All people seem to need data processing. If you search on Google, I'm sure you can find some other mnemonic devices. At present, some teachers need Dr. Phil is a good one. There's a few funny ones that I'm not going to say on the video, but it can get confusing. And then you have the TCP/IP reference model. So the OSI reference model, in order to get it right, you might have to study a few times, looking at the various layers and then employing a mnemonic device. But we're going to go ahead and we're going to talk about each of the layers individually. So let's begin by talking about how each of the individual layers behave. So first, layers exist to encapsulate a specific functionality, and they provide services to that layer alone, and they deliver data or accept data from the layer below. Again, a protocol stack is a great example of a design that's used as part of the OSI model. And protocol data units, they envelop information in this form of specific headers and trailers. All right, so let's talk about these 7 layers. This is one of the most important things that you're going to need to get a grasp of. So it's important that you understand the basics. The physical layer is the lowest layer of the OSI model. These are the interconnections, either electrical or optical or even wireless. We're talking about radio waves as well, to allow data to transmit between devices. And we're talking unstructured bits, ones and zeros, across these mediums. So this layer is concerned with cabling, pin layouts, radio frequencies, voltages. It talks about cables, hubs, repeaters, network adapters, modems. This is all the electronic bits and the wires for those bits and the wireless receivers for those bits. That's the physical layer. The data link layer is next, and this is where you're directly connecting nodes together so you can transfer those bits between two devices. And the breakdown terminology in terms of that are called frames. That is the package. We take the bits from the physical layer, we package them into frames. It also corrects certain errors that might have occurred at the physical layer. In the data link layer, there are two sub-layers. First is media access control. So you've probably heard of MAC addresses. That is the address at the data link layer to allow for flow control of data, device transmissions for multiplexing over a network. And the next is the logical link controller, LLC, and that's flow and error control when looking at that physical medium, as well as specific protocols for various types of lines. So that's the data link layer. Next up the chain is the network layer. Now this is responsible for grabbing those frames in the previous data link layer and delivering them to specific destinations based on their addresses. So this is where we have another abstraction of your address or your representation of a device. So at the data link layer, we have the MAC address, and at the network layer, in this course, we have the IP address. That is where we're trying to send from or send to. And routers live in this layer 3 or network layer. They route the information from point A to point B and everywhere in between in order to get from point A to point B. Next up the chain, layer 4 is the transport layer. And the transport layer, it manages delivery. It manages air checking, and it manages the sequence of packets, the size of packets, and the transfer of data between hosts. And this is where TCP resides. It wants to make sure that data gets from point A to point B reliably, and that's the transport layer. Now let's talk about the session layer, or layer 5. And this is the layer that controls logical connections, and it provides inter-process communication between two systems. So if you've heard of remote procedure calls, that protocol, RPC, lives in this layer. It attempts to resolve failures of meeting similar problems, and the session layer services organized data exchange. So you have recovery points or fixed points where sessions can be synchronized after a failure, can be restarted without having to begin a data transfer from the beginning again. The presentation layer, or layer 6 of the OSI model, manages syntax and semantics of information exchanged between two platforms. It's generic and network-oriented forms of expression to make sure that data can be handled and understood between two systems. Languages can be different between the two systems, but the presentation layer itself acts as a translator. So the presentation layer performs translation. So before transmission, it can change various bit streams and numbers. It's responsible for interoperability. It can handle encryption. So it can carry out encryption or decryption between the sender and the receiver. And it can also manage data compression. So it can reduce the bandwidth of the data being transmissions by either the sender or receiving end, compressing or decompressing that data. Finally, layer 7, we have the application layer, and the application layer is responsible for manipulating data in various ways to allow the end user or software to gain access to the network. So services in this layer you see all the time: emails, file transfers, directory services. It handles various protocols that you're familiar with, so HTTP or Hypertext Transfer Protocol, File Transfer Protocol or FTP, SMTP, the Simple Mail Transfer Protocol, Telnet, DNS, everything that you're used to seeing. This is the topmost, highest level of the networking environment and the OSI model. The TCP/IP networking model, like the OSI model, is an abstraction, but the OSI model differs from the TCP/IP model in the ways the layers are defined. The transport layers in both models are the same, but the network layer differs from the OSI reference model as well as the internet layer in the TCP/IP model. So we're going to go over the differences of these two models and how they relate. So in the diagram on your screen, on the left is the OSI model, all 7 layers, and the 4 layers of the TCP/IP model are on the right. So the network access layer of the TCP/IP model represent the conglomeration of physical and data link layers of OSI. The internet layer is equivalent to the network layer in the OSI model. The transport layers are the same, and the application layer represents application, presentation, and session within the OSI model. The network access layer in TCP/IP, also called the network interface layer, it's everything in the OSI model that we talked about, Ethernet, Cat5, token ring, wireless media, so the radio frequencies, wireless access, point-to-point protocols, and any of the IEEE standards for networking apply to this specific layer. But remember, it encapsulates the 2 layers, the data link and the physical layer of the OSI model. Various protocols used in this layer in the TCP/IP network model. PPP, point-to-point protocol, it's the most important TCP/IP network access layer protocol. PPP over Ethernet, widely used on Ethernet networks or networks using Ethernet characteristics, and other protocol suites, HDLC, frame relay, and asynchronous transfer mode. The internet layer functions of TCP/IP, this is the routing between machines across multiple networks, and there's 3 tasks here: MTU, fragmentation, addressing, and routing. And we're going to dig into all of this in later chapters as we look to how these various reference models can be applied to some more real-world situations and network designs and the TCP/IP protocol. So other internet layer protocols, IP, we've talked about. ICMP, the Internet Control Messaging Protocol. Ping, we all know Ping. ARP, and reverse ARP, which we'll talk about later. The Bootstrap Protocol, BootP. Routing Information Protocol, Open Shortest Path First, and BGP, or Border Gateway Protocol, which you've probably heard of in terms of large internet networks and how information gets routed over and across multiple networks. So the transport layer functions, again, we want to make sure that data that we're delivering, that it's reliable when the sender sends it to the time the receiver gets it. And that segmentation of outgoing message and the reassembly occurs before their delivery to the application layer. And hosts in this case are any devices that operate on the internet. 2 important protocols to consider in the transport layer: TCP, again, part of the goal of this course. Again, it's connection oriented. We talked about reliability. And then the user datagram protocol, which is a connectionless protocol. It's a best effort delivery. It's not really focusing on reliability, and it doesn't follow up on whether or not the data has been received. But again, here we're focusing on TCP. The application layer in the TCP/IP model is also called the process layer. Services depend on it, listener processes or daemons. So it sits on a server and awaits for user requests in order to provide various services that the server was designed for. Port addresses, so every TCP/IP service has an associated port address, and that allows for further segmentation at the communication layer. And protocols and services, sockets and ports, so multiplexing. That's where you combine various sources of outgoing data into a single output data stream. Demultiplexing is breaking up an incoming stream, so separate portions can be delivered to different applications. And then well-known protocols, they assign a series of numbers to represent a large collection of TCP/IP-based network services. So again, all of this will be covered in later chapters. Various protocol numbers. There's a table here that I'm showing you on basically how protocols are numbered. So whether it be IPv6, gateway to gateway protocol, the transmission control protocol, each of them are represented by various numbers. So it's good to familiarize yourself with some of these numbers and their associations. But again, we'll dig into this as we go through the rest of the chapters in this semester. Again, here's some more protocol numbers that you can familiarize yourself with as part of this chapter. But again, um, this is something we're going to go into more detail later. TCP/IP port numbers. TCP/IP application processes are sometimes called network services, and each of these services are identified by port numbers. So you have a source port number and you have a destination port number. The source port number, that's the identifier for the process that is sending the data, and the destination port number, that identifies the process that's going to receive the data. TCPIP sockets, these are a combination of an IP address and a port address. So well-known or registered ports, these are pre-assigned port numbers. Socket addresses, it's a combination of an IP address and a dynamically assigned port address. So this is basically, if you hear the term socket, this is what it means. Data encapsulation in TCP/IP. So in each layer of the protocol stack, outgoing data, it's going to be packaged and it's going to be identified before it gets delivered to the layer underneath. So there's two main parts. You have your header, packet header. Each PDU's, this is their opening component. It identifies which protocol you're going to use, who sent the PDU, and who is intended to receive it. And then the trailer provides various data integrity checks. And protocol analysis, that's the process of tapping into network communication systems, capturing packets, gathering statistics, decoding them, essentially eavesdropping. But when we talk about headers and trailers and the data packets, the protocol analysis process, these are going to be revealed when we analyze various protocols and the data transmissions. So why would you want to perform protocol analysis? We could use it to troubleshoot network communications. It's to test networks, so either active or passive testing, and we'll look at how those breakdown works. Gather trends on network performance, analyze availability for a variety of platforms. One of my focuses is cybersecurity, and protocol analysis in my case is looking for anomalies or strange behavior. So it's useful in many realms for troubleshooting, for auditing, for cybersecurity analysis. It's used pretty much everywhere and anywhere, and it's something you need to be familiar with. Elements of a protocol analyzer, a promiscuous code mode card and driver, packet filters, trace buffers, decoders, alarms, and statistics. When you hear about the various features of a protocol analyzer, these are going to be the main features within it. So here is where these elements kind of sit in terms of how a protocol analyzer works. So you have data on the line. It goes through your promiscuous mode card, up through your driver. It goes through a capture filter, and then it goes into the trace buffer. The display filter then breaks it down further so you know what you want to see, what you don't want to see, and then you see a subset of your traces. And you can use the overall filter to save this to your disk. Here is an example of a protocol analyzer window, how you would use it through a GUI. In here you have a packet list pane, packet details pane, packet bytes pane, and in the labs you're going to dig into how to use a protocol analyzer, how to read the data, but here's a screenshot of Wireshark to show you how to, or how it would look if you were analyzing some packets. And again, here's another picture of from Wireshark. You can use it to look at traffic rates or other statistics. You can even take the data out of Wireshark and bring it into another program if you wanted to, even throw the data in Tableau or Power BI to perform some detailed analysis, especially if you're looking at different behaviors or different trends that you're trying to identify. You don't have to necessarily do everything in Wireshark. You can pull the data out and do some larger analysis on it. And then when you put a protocol analyzer on a network, the analyzer itself, it captures the packets. On networks with hubs, you can really put it anywhere on the network because of the way hubs are designed. And then for switch networks, you either need to hub out the network, you need to redirect ports or do remote monitoring. So there's other strategies that you have to take on switch networks. So here's an example. If you have a switch network, you could have a remote monitoring agent that resides in the switch, and this agent can then forward packets to your packet analysis system. And from that point, you can analyze the packets, download the packets, save the packets to disk, do whatever you need to do, but it's a different setup than a normal hub network. So in summary, TCP/IP design goals, we want to make sure that we're supporting multiple packet switch pathways to the network. We want to allow different computers, no matter how dissimilar they are, to exchange data, and we want to be robust. We want to make sure that when we send data, it goes from A to B and it gets there reliably. And we want to provide comprehensive network access no matter what the size of the network, so on a global scope. So we talked about the initial implementations of TCP/IP and all the history on that. It's good to know a little bit of background. And remember, TCP/IP is in the public domain, but there are approval bodies that look at standards and set best practices. And because of the size of the original IPv4 network space, IPv6 is the future. It has a larger addressable space for all the devices in the world that IPv4 can no longer support unless it's all behind a NAT. And the OSI reference model, this is huge. You need to remember it. It breaks the network into 7 distinct layers. Recall the TCP/IP's reference model takes parts of the OSI, puts it in different layers, and make sure you understand the mapping between the two. And then we cover protocol analysis, which you're going to experience in some of your labs. So this was a general overview of Chapter 1. I tried to walk through, and I'm going to do this for every chapter, walk through the key points in the chapter, make sure that you're reading the text, doing the labs, and taking the quizzes. That is the source of truth for this course, is the textbook, the labs, and make sure that you are going through them and thinking about them. As I said in our introduction to the course, this is going to be core to everything going forward in your career, and some of the information can be really dry at times. Hopefully I can intersperse some jokes in some of these chapters, but remember, this really is about reading, it's about absorbing, and it's taking in a lot of information in a short period of time. So again, dig in and focus for the semester. Realize this probably isn't going to be the most fun course you take, and my apologies for that. I have other courses I teach, like the cybersecurity scripting course, which are probably a bit more fun. But this is one of those things you need to understand in order to really get the rest and master the rest throughout your career. So dig in. If you have any questions on the videos, if I accidentally misspoke on the video or you notice something I need to make a change, please let me know. If you have any questions, please contact me. Again, this is all laid out in the syllabus, but hopefully this is a good primer and a good summary of the information that you're going to go through this week. So again, if you have any questions, let me know. Otherwise, good luck with this week's material.